All right, we're going to pick up now by taking a look at the limit comparison test. So let's take a look at what this says and see how it kind of compares and contrasts with the idea of the comparison test. Here's the statement of the theorem. Suppose, again, we have two series, an A sub n series and a B sub n series, and that these are series with positive terms. So I'm going to specifically require that each of the numbers in these addition problems are positive numbers. Negatives are not allowed. 0 is not allowed. Okay. Then we can go ahead and state the following. If it's the case that when I do the limit as n approaches infinity of A sub n over B sub n, and let's suppose that I crunch out that limit and I get the value of C, where C is a positive finite number, then both series will either converge or both will diverge. This is a very, very interesting statement. All right, if we think about what this is actually saying, it says, okay, suppose you have two series, only positive things in their addition problems. If I take the two formulas out of those series and I divide them, the order of that division doesn't necessarily matter. But if I apply a limit to that and I get back a number that's positive, that's finite, then for some reason I'm able to conclude that these series have the same behavior. That is, they both converge or they both diverge. Now we're going to go ahead and attempt to try to justify that by taking a look at what we have down below. All right, so here's what I'm going to go ahead and do. Let's suppose that we're already working with series that meet all the above conditions, okay? And we can already suppose that the limit of A sub n over B sub n does indeed equal C. Again, where C is a positive finite number. Now, I'm going to go ahead and attempt to draw a quick picture here of what's kind of happening. So this is not a picture in the XY axis, but this is a picture of n on the one axis. And on the other axis, I kind of have my A sub n over B sub n things. Again, this A sub n over B sub n kind of creates like a brand new sequence of dots that I could put in this picture. And I'm told that they go towards the value of C. So let's just pretend, for the sake of argument, that the value of C is right here. Maybe this is the value of C. And maybe it's the case that my A sub n over B sub n dots continue to get closer and closer and closer to what I have. Okay, so that's the limit. Well, I think I could go ahead and I could make a couple additional arguments. Here's what I could also say. Then there are positive numbers, I'll call it little m and capital M, such that this value of C could fall between these two values. If C is a positive number, then it's got to be somewhere like in the picture. It can't be on that n axis. It's got to be above it. But then that means that like there's got to exist some value that I could draw that's lower than it, and some other value I could draw that's higher than it, right? I kind of sandwich the C in. Okay, but I could then also say this. Since the limit of A sub n over the B sub n is equal to C, we know there is an integer capital N such that my dots, A sub n over B sub n, will be between the m's when n is past my green capital N. You can maybe almost see in the picture where this occurs. It looks like if I went and picked any value on this little n axis that's past the value of the green n, I start to see all my dots eventually there are fitting inside of the blue boundaries. Not all dots fit inside the blue boundaries, but if you go far enough down the list, if you go past green n, eventually you get inside. But of course, if this is a statement that I can clearly make, I can then go ahead and modify it slightly. I'll say this implies that if I took my b sub n value and I multiplied it kind of from this inequality over here at the side, I multiplied it all the way through, I could get that the following is true for all n greater than or equal to n. Okay. Now, again, I can multiply that. I don't have to worry about flipping inequality signs or anything weird like that because b sub n only had positive numbers in it. Okay. Here's then some really cool things that we could start to actually say. I'm going to break this down to kind of 2 bullet points. Let's suppose that the series with the b sub n converges. If it's the case that b sub n converges, I have no idea if it does or not, but if it did, then I could go ahead and state that the series with capital M b sub n also converges. Notice it's just the same series, just multiplied by a constant. But then, since this series and the a sub n series have definitely only positive things, and therefore non-negative things, I could say thus, by the comparison test, the series of a sub n converges. Because notice again that capital M b sub n is bigger than the a sub n. So that's the smaller bit, it's got to converge. Now, of course, that was all predicated on this big if of if the b sub n converges. Maybe it does, maybe it doesn't. But if it doesn't, then of course the only other option is that that series diverges. But if it diverges, then definitely the series multiplied by little m also diverges. Because, well, it's the same series, just multiplied by little m. But notice if this little series diverges, you can make a similar argument by the comparison theorem that a sub n has to diverge as well. So therefore, by the comparison test, the series where a sub n diverges. So notice that we can see in here that we have this kind of similar behavior. If b sub n converges, a sub n converges. If b sub n diverges, a sub n diverges. So by knowing what happens with that limit, I automatically see this result pop out. This is really powerful, and this acts as kind of like a proof of the, or this acts as the proof of the above theorem. Okay. In the next couple examples, we'll take a look at together how exactly we can utilize this in some specific cases.